All right, so number 9 on the final review says to find the monthly interest payment. So it says you maintain an average balance of $750. So our average balance is $750 on our credit card, and it carries a 24% annual interest rate. Ouch. That hurts, 24%. What that means is over a year, you're going to pay 24% of that balance extra in interest, right? So in order to solve this one, you are going to be using one of the formulas off of your formula sheet. Again, it's not one that you have to memorize. It's under simple interest. It's I equals PRT. You don't have to memorize it, but you do have to know how to use it. So P represents our principal, or in other words, our balance. R is our rate. R is our rate, so that would be our interest rate, our 24%, and T is the time in years. And then I, of course, is the interest, and that's what it's asking for. It doesn't want total payments or anything like that. It just wants to know if you're just paying the interest. So I equals PRT. So mine's going to be, my I is going to equal $750 multiplied by my rate, which is 0.24, and then I multiply that by the time. And when my time is in years and it's asking for my monthly payment, that's 1/12 of a year. Okay, that's 1/12 of a year. Not 1 year, because it's not a full year. We're looking at the interest payments each month. So I'm going to put 1/12. So when I go to my calculator and I do 750 times 0.24, and then I'm going to times by 1/12, and that's going to give me $15. That's our units in dollars, right? That's how much we're paying. So every month you would be paying $15 in interest back to the credit card company. Okay, number 10 is the same thing. 10 is the same thing, interest payment, but on this one, your balance, well, on mine, my balance is $525, and again, my interest rate is 24%. So interest equals my balance times the rate times time. It's the I equals PRT. And because it wants monthly payment, I'm going to do 1/12 because I'm looking at 1/12 of a year. So I'm going to go back. I'm going to do 525 times 0.24 times 1/12. And I get 10.5. So when we're talking about money, 10.5 is $10.50. So you'd put 10.50. It does the dollar sign for you. Again, be really careful when you're putting in these answers that you take the time to put it in correctly. Don't do all this work and then put the answer in wrong. Number 11, use the appropriate compound interest formula to compute the balance after a period of time. So it tells me that $25,000 was invested. Again, this is my numbers. $25,000 is invested for 6 years with an APR of 4%, and it's compounded daily. Okay, it's compounded daily. And all of this is information that we're going to need to know. All right, so again, we're using one of the formulas off of our sheet. You don't have to memorize it, but it's under compound interest. And the formula that we're going to use is the A equals P multiplied by 1 plus R over N raised to the NT. Now, the reason that we're using this one is we are looking for the balance at the end of the time, which is our A. Okay, A is kind of like our accumulated balance, how much money we have total after a certain amount of time. So P is our principal, what we started with, just like it was in the other problem. N, we got to be careful. This is the number of compounds a year. It's the number of compounds in a year. And if I'm compounding every day, then my compounds per year is going to be 365. Okay, my R, my rate, is my percentage, so 0.04. We're going to write it as a decimal. My N, again, is 365. It hasn't changed. It's still N. And my time is years. T is for years. And we are investing on mine, again, it's for 6 years. So my formula is going to come out as A equals 25,000 multiplied by 1 plus 0.04 divided by 365 raised to the 365 times 6. Now, when I put this in my calculator, because I don't want to do it in my head, I want it to look exactly like that. So when I put it in my calculator, I'm going to take the time, 25,000, and then I'm timesing that by 1 plus, I'm going to go ahead and put it in as a fraction, just so I know that it looks like what it's supposed to, 0.04 on top, 365 on the bottom. And then on the outside, I'm raising this. Now, we got to be careful that when I raise this to the 365 times 6, that both of those numbers stay up in the exponent. The 365 times 6 needs to stay up there. If you need to put parentheses around it to make sure that both of those numbers are up there in the parenthesis or up in the exponent, go ahead and do it. I hit enter and I get 3178.81, 0, blah, 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 blah. And it wants me to round to the nearest cent. So when I go back, my answer is going to be 31,780.81. Remember, we're rounding money, we're rounding to the nearest penny. And this one was nice because after the 81 was a 0. So that rounding is one hopefully we're not messing up. Okay, number 12. Number 12, we use the same formula, but this time, mine says that we're investing $7,000, and it's for 13 years. My APR is 5%, and I'm monthly compounding. So I'm compounding 12 times a year because I'm compounding every month. So I'm going to use the same formula. A equals P, my principal, 7,000, multiplied by 1 plus 0.05 over, I'm compounding monthly, so I'm going to put it over 12, raised to the 12 times 13. I'm going to plug it in that same way I did before. I'm not going to take the time to do that. You just watched me do one of those. If you didn't, go back and watch number 11. You plug it in the calculator and you get $13,390.69 when you round it correctly. Again, take the time, do it right. Number 13. Similar question, very different formula. Okay, this one says use the savings plan formula below, or use, not below, it's below because I gave it to you. Use the savings plans formula to answer the question. So your goal is to create a college fund for your child. You have 5% interest, APR. How much should you deposit monthly to accumulate $84,000 in 14 years? And it's asking for the monthly payment. It wants my monthly payment. So I go to my formula sheet and I go down to annuities because that's what we're going down to, what are we compounding? It is under annuities. That is where it is. So it's P equals, because we're looking for the payment. There's two formulas under annuities. There's A, which gives you the balance that you've accumulated. Or there's the P formula, which gives you your payments every month to save up a certain amount of money. So I'm looking for my payment. I want to save up. Oops, let me give you the formula first. Then we'll start plugging stuff in. So it's A multiplied by R over N, all divided by bracket 1 minus 1 plus, oh, I'm writing down the wrong one. Bracket 1 plus R over N raised to the NT minus 1, close bracket. All right, so when I plug in my numbers, I'm looking for the payment. I want to save up $84,000, and my interest rate is 0.05. My number of payments, my N is my number of payments. I'm just making payments every month, so that's going to be 12. And then big fraction bar, and on the bottom I've got 1 plus my rate, 0.05 over my payments, 12, raised to the 12 times the number of years. Remember, T is the number of years, so 14, and then I'm going to minus 1. So this one is a little bit uglier, right? This one doesn't look quite so pretty when you're trying to plug it in. So I am going to, again, I'm going to work really hard to make sure it looks exactly like the formula. So I'm going to do my big fraction bar, and on top I'm going to put my A, which was 84,000. Parenthesis, I'm going to put another fraction bar in. Some of you can do this without the fraction bars. I just want you to see that you can make it look exactly like you should, or that you can make it look just like it looks on your formula sheet. So A times R over N, and then I'm going to put parenthesis 1 plus R over N, so another fraction bar, 0.05 over 12, and then I'm going to close that parenthesis, and I'm going to raise that to the N times T, so 12 times 14. Again, all of that needs to make sure it stays up in the exponent, the N and the T, minus 1, close parenthesis. When I hit enter, I get 346.251. So if I round that to the cent, to the nearest penny, then that's going to equal $346.25. So if you wanted to save up $84,000 in 14 years, you would need to put $346 in the bank every month. Okay, number 14. Getting away, no new formula, same idea. At age 45, you start saving for retirement. You get 6% interest. You want 0.9 million in 20 years. So I've got 20 years and I want to save up 0.9 million. I don't like that number, 0.9 million. If I turn that into, instead of 0.9 million, because if I put 0.9 million in my calculator, it's not going to work. So I'm going to put 900,000. If you don't know how to do that, you do 0.9 multiplied by a million. And you get 900,000. So that is how much I'm trying to save. I've got my years, I've got my interest rate. It wants to know how much I should deposit monthly. So I'm going to use the same formula that I used in number 13. P equals A times R over N divided by bracket, parenthesis 1 plus R over N raised to the NT minus 1. So same formula. I'm going to plug it in just like I did on number 13. I'm not going to take the time to do that. Again, you just saw me do it. You can plug it in yourself. When you get the answer, you get $1,947.88 each month. So if I wanted to save almost $1 million in 20 years, I'd need to put about $2,000 in the bank every month into that savings account. okay? If you need to see putting that in the calculator, go back and watch number 13 again. I just don't think everyone needs to sit through watching me type it in the calculator every time. So number 15 wants me to consider a student loan of $17,500. Okay, so my loan is $17,500. It's got a fixed APR, so my interest rate is 9%, and it's going to take 15 years to pay off this loan. So it wants me to do a couple of things. Calculate the monthly payment. It wants my payment, and then it wants the total amount paid over those 15 years. And then it wants the percentage that was principal and the percentage that was interest. Okay, so there's a lot going on in this problem. First things first, monthly payment. Now, I am borrowing money. I'm not putting money in a savings account. So this is an amortization problem. So you should be using your amortization formula. And the one that I'm using, I'm looking for the payment. So PMT equals P times R over N, all divided by bracket 1 minus 1 plus R over N raised to the negative NT. So 1 minus 1 plus R over N. It's weird to do a 1 minus 1 plus. And so this is the formula that we're going to use. Again, you don't have to memorize the formula, just know how to use it. Know what it does when you use this formula. So I'm looking for my payment first. So I take the balance. P represents the balance, the amount of money that I'm borrowing, so $17,500. R still represents the interest rate. N represents the number of payments every year, so 12, because it says I'm making, what's it say, monthly payments. So N is the payments. And then I'm going to do a big fraction bar, and on the bottom, bracket 1 minus, parenthesis 1 plus, 0.09 divided by 12, raised to the negative 12 multiplied by the number of years. And my number of years was, where'd I write it? Oh, 15, right there. So great big ugly formula. I'm going to plug it in the calculator. I'll go ahead and show you this one. Again, I'm going to do a big fraction bar. And on top, I'm putting my borrowed amount, $17,500. And then interest rate is, let's do another fraction bar so we can make it look the same. 0.09 divided by N, which is 12. And then I'm going to do parenthesis 1 minus parenthesis 1 plus my interest rate, 0.09 divided by my payments, 12. And then I'm going to raise that to the negative 12 times my number of years. And what did we say it was? 15 years, right? So things to be careful of, make sure the exponent is the N and the T being multiplied up there. When I hit enter, I get 177.4966. So 177.4966. Now I'm rounding to the nearest penny, so that's 177.50. And that's going to be my monthly payment. So that's my answer for part A. That's my payment, my PMT. That's my payment every month to pay off that money that I borrowed. Now, part B wants me to find the total amount that I paid. So I take my payment and I times it by the number of payments that I made. Well, I made a payment for 15 years every month. So I'm going to do my payment amount times 15 times 12. So 177.50 times 15 times 12, and I get 31,950. Yikes. $31,950. So you borrowed $17,000 and you paid over $30,000 back to the same bank that you borrowed the money from. That's a lot of interest over 15 years. You're paying almost double what you borrowed. Man, banks make a lot of money. So again, in order to do that, I took my payments and I multiplied it by the years, and then I multiplied it by the months, by 12, okay? For part C, so let's see, that's the answer to part B. For part C, it wants us to find the percent that went towards the principal, okay? So in order to do that, I'm looking for a percent, and I'm looking for the percent of the total amount that I paid that went toward the principal. Well, the principal was $17,500, and the total that I paid was $31,950. So that's what goes on the bottom. And this is going to give me the percent of the total amount that went towards the principal. So $31,950 on the bottom. And I get 0.5477. So let's see, 0.5477. Now it wants this written as a percent rounded to the nearest tenth. So as a percent, this is 54.77%, but it wants it rounded to the nearest tenth. So that's going to be 54.8%. So that would be the first part of my answer. And then it wants to know what's the percent that got paid toward interest. Well, if 54.8% got paid toward the principal, then that means the rest of it got paid toward interest. So I'm just going to take 100% and I'm going to minus 54.8%. And when I do that, I ended up with what? 45.2% is how much went towards interest. So almost half the money that I paid went towards the interest, okay? All right, number 16 is exactly the same. The interest rate is going to change. The number of years is going to change. For 16, I'm going to set this up, but I'm not going to walk through the full solution. I'm borrowing $17,500. My rate is 6%, and I'm paying it off in 30 years. So I'm going to use that same PMT formula that I used before. P times R over N, all divided by 1 minus 1 plus R over N raised to the negative NT. So the formula that I would use is PMT equals 17,500 times 0.06 over 12, because I'm making monthly payments. And then on the bottom, I would get 1 minus 1 plus 0.06 divided by 12, raised to the negative 12 times my number of years. This time I'm paying it off in 30 years. I'm going to take 30 years to pay off $17,000. That's a long time. So when I put that in my calculator, my answer comes out to be $104.92. So that would be my monthly payment. Then to find out the total amount that I paid, so that's my answer to part A. My total amount that I paid, I would take that payment and I would times it by monthly, times it by the number of years, and my total comes out to be like $771.20. So you borrowed $17,000 and 30 years later you paid it off, and it cost you almost $40,000. For part C, to figure out the percent that went towards the principal, well, I borrowed $17,500 and my total was $37,771.20. So I divide that and I get 46.3% that went towards the principal, which means 100 minus 46.3, which is 53.7%, is what went towards interest, okay? All right, if you need to see that one done slower, go back and watch number 15. We go through that one a lot slower. So, all right, number 16. 16 says Oh, wait, that was number 16. 17. 17 is a little bit of a story problem. It gives you, well, I guess most of these kind of are, right? It tells me that a recent phone company polled 1,001 women. So there was 1,001 women that it polled, and it said that 6 in 10 of them believe there is progress in finding a cure for cancer. So they say there is progress. Awesome. Describe the population, the sample, the population parameters, and the sample statistics. This is one most of you are going to be able to figure out on your own. The population is the total group that it's studying, okay? And it's studying all the women in the country, right? Clearly, it's selecting women from the country, and it's asking them if they believe that the cure for cancer has made progress. So their population is all the women in the country. The sample is basically the group that they interviewed, or the group that they asked the questions to, the group that they polled. So their sample is the 1,001 women that they asked, that they selected. Okay, the population parameter, remember, is what are they measuring? What is it that they're looking for? Or what is it that they measured in the poll? And what they measured was the percentage of women, of all women in the country who believe there is progress. So that's what their parameter is. That's what they're trying to figure out, right? The percent of women that believe there's been progress. And the sample statistic is just what the sample told them, the stats from the sample. So the sample statistic was 6 out of 10. Okay? That problem, I wish that there was a way around getting through all the reading that you're going to have to do on these next couple of problems. Number 18 is the same thing as 17. I don't think we need to walk you through that one. If you're stuck on 18, go back and watch 17. Number 19, determine whether the following variable is qualitative or quantitative. So qualitative or quantitative. Remember, quantitative is numerical. Okay, it's numerical. It's something that you can measure. Qualitative is not. So for me, number 19 says the flavors of ice cream at an ice cream parlor. It's not saying the number of flavors. It's just saying the flavors themselves. Well, flavors are not numerical, so I would say that it's qualitative. I would say that it's qualitative because flavors are not numerical. And that's it for number 19. Quick and easy, right? Number 20, same kind of question. Is it numerical or is it qualitative? This one asks, at least for me, it asks the salaries of NBA players. What are the salaries of NBA basketball players? This is definitely quantitative because salaries is numerical. So I would say it's quantitative because salaries are numerical. And that's it for number 20. Hopefully that one's on the final. Give you a couple easy ones there. Number 21, for the following pair of variables, state the units that you would measure, then whether you believe they're correlated. All right, so latitude and the average temperature in June. Okay, so in order to measure latitude, if I'm measuring latitude, I would use degrees of latitude. Latitude and longitude are measured in degrees of latitude or degrees of longitude. To measure temperature, I would use degrees of Fahrenheit. Okay? Don't mix those up, right? Degrees of latitude is not a temperature degree. It's the degrees of where that latitudinal line. I don't even know how to say that word. They're both degrees. They're not the same degree. So be careful there. Now, it asks if there's a correlation. Now, remember, a positive correlation tells us that as one goes up, the other goes up. A negative correlation says that as one goes up, the other one goes down. And no correlation says they just do whatever the heck they want. So in June, in the summer, if you think about latitude, now latitude is north and south. So as I go further north, as my latitude goes up in June, what does my temperature do? If my latitude goes up, my temperature goes down, right? As I move further north, as my latitude goes further north, then the temperature is going to go down. And the opposite, if I go further south, then my temperature is going to go up. So there is a correlation, and it's a negative one. It's a negative correlation, okay? Number 22. My question is, if I can find it here, same question, are they correlated or not? And it's asking me to compare the height and how frequently a person goes to concerts and the frequency that someone goes to a concert. All right, so to measure height, I'm going to use feet, right? To measure height, I'm going to measure feet. I'm not going to use liters or degrees because I'm measuring height. That's a distance. To measure the frequency that someone goes to a concert, I'm going to use the number of concerts that they went to. What word does it use in the problem? Attendances, number of attendances. That makes sense. Okay. And are they correlated? Or in other words, as you get taller, do you go to more concerts or less concerts, or does that have nothing to do with how tall you are? I would say that there's definitely no correlation. All right, you might argue, if you were to actually sample people and you asked a bunch of short people like younger kids, it might look for a minute like they go to less concerts, but that wouldn't be a very good sample if you were only asking if you weren't categorizing your group that way, right? If you were just lumping kids in with adults and asking them how many concerts they go to, that might not be a very good sample right there. Okay, let's see, where are we at? Number 23. I know these are running long. They're long problems, and there's a lot of them. So consider the distribution of the annual rainfall. Let's see, rainfall in 110 cities randomly selected throughout the United States. Okay. How many peaks would you so when it says consider the distribution, it wants to know if you looked at this data, what's it going to look like? Are you going to have 2 peaks? Is there going to be some cities with very little rainfall, some cities with a lot? And then is there going to be groups like this where it gets really high and then something in the middle? Or is it going to be distributed evenly? Are you going to have some cities with very little, some cities with a whole bunch, and then the rest of them kind of average out, centered around some amount? I would definitely go with the 1 peak. Okay, there's not a lot of obvious reasons when you're picking cities all over the country. A few of them aren't going to get very much rain. A few of them are going to get a whole bunch of rain, but most of them are going to be somewhere in the middle. There's no reason that you would have more than 1 peak, okay? If it wants a sketch of the distribution, well, you're just drawing a sketch of a peak. Ta-da. So pick the one that looks like that. Part C, what shape would you expect for the distribution? Now this one, part C is going to get a few of you. What it means, we already know what it looks like, but what it means by what shape would you expect is it going to be skewed to the left? Is it going to be skewed to the right? Or is it going to be perfectly symmetrical? Now we've got to be careful on these because a lot of you are going to pick that it's symmetrical. It's this one right here in the middle. But this one is actually going to be skewed to the right. And the reason it's going to be skewed to the right is because there exists a minimum. Okay, what that means is, what is the smallest amount of rain that you could get in a city? Well, it's 0. And then it goes up from there. But there is no maximum. There could be a city that rains every single day, clear up here all by itself. Somewhere in what, Washington, right? But there can't be a city that rains in the negative direction. So this data is going to be skewed to the right because it can only go so low before it stops, but it can go up forever. So it's going to be a right skewed distribution is the way that we word that. It's a right skewed distribution. Now part D, oh my gosh, this problem is still going. And reading through these answers, I'm glad I'm not taking this test because all of them are a sentence or two. So part D says, what variation would you expect in this distribution? Now remember, the variation is how far spread out do you expect the data to be? And I would say that there would be a large variation for sure, because again, some cities are going to get very little, and there's some cities that are going to get a whole bunch of rain. So the variation is going to be very large. It's not like if it was saying, let's pick a bunch of cities in Texas and compare the rainfall. In that case, it might be a little bit more equaled out. It's asking you to compare all cities in the U.S. So that variation is going to be huge. Number 24, guys, it's exactly like 23. I'm not going to read through another one of those. We're going to go ahead and move on to number 25. If you're stuck on 24, see number 23. Although if you could do one, you can probably do the other. So I don't know if that's going to happen. Okay, number 25. After recording the pizza delivery times, you conclude that one pizza shop has a delivery time of 44 minutes and a standard deviation of 3 minutes. Okay, so pizza shop A has an average delivery of 44 minutes and a standard deviation of 3 minutes. So remember, what that means is on average, they get there in 44 minutes. And the standard deviation tells you how spread out the rest of the data is. So this is telling me that most of the data is within 3 minutes of that 44-minute average, okay? Then it tells me that pizza shop, a second pizza shop, I wish it gave it names, has an average delivery time of 41 minutes, but it has a standard deviation of 19 minutes, which tells me that some people get their food in 22 minutes, but just as many people don't get their food for an hour. So the average is a little bit lower, but the variety, the distribution of the times is a lot more spread out, okay? So for part A, you would say something like the averages or the means are almost equal, but the variation is a lot greater. But the variation is greater for the second pizza shop. And what that means for part B is it says if you liked pizza from both of them the same, which one would you order and why? Well, that sounds pretty opinionated, but what it wants you to say is that you would choose the first because the delivery time is more reliable. It has a lower standard deviation. That's what it wants you to choose, but maybe you don't. I don't know. Maybe you would rather just try to get your food. Maybe you don't care when it comes. I don't know. It's probably the best answer. Okay, number 26. Similar question. You have two airlines. Does it give these ones names? Okay. So an arrival time of plus 4 minutes means the flight arrived 4 minutes early. Okay. So Sky High has an average arrival time of -5. So that means it's -5 minutes late. So it's 5 minutes late on average, and it has a standard deviation of 4 minutes. Now, Skyview Airlines has an average arrival time of 0.5. So that means it's 30 seconds early on average. On average, it's 30 seconds early, but it has a standard deviation of 9.5 minutes. So this one's going to ask you the same thing. It wants you to explain what this means. Well, what this means is that Sky High is late. Sky High is late on average more often, but when you look at how spread out the data is, it's a lot more reliable because there's only a 4-minute average standard deviation. So if you were wanting to avoid delays, then Sky High would be your best option, right? If you don't like your flight coming in way late or way early, you like being on time and you would choose Sky High. Okay, Skyview runs ahead of schedule, but it can also have a lot of delays. It could also run behind. It happens quite a bit. Okay, number 27. Use the table of standard scores and their percentiles. Okay, so 27 wants a data value in the 30th percentile. All right, so what that means is I'm going to pull up my table. And where is my table? Oh, I do have one. Okay, so I'm going to pull up my table, and I'm looking for the percentile that's closest to 30th. So as I go through when I click, there's a link, there's the little icon that you click on and it'll give you the table. You don't have to memorize the table. When I go to my 30th percentile, I've got 29.12 and I have 30.85. This one is closer to 30%. So that's the one that I'm going to use, 30.85, and my z-score, what I'm looking for is the z-score that goes with that. My z-score at 30.85 is -0.50. Now what that means, so that would be my standard score, -0.50. What that means is that the 30th percentile lies 0.50 standard deviations below the mean. So you've got to put this and this in. The negative tells me that it's below. So it's 0.5 below the mean. All right, so for part B, I'm using the 90th percentile. So 90th percentile, if I look at the table, the closest one to 90 is 90.32, and that gives me 1.3 z-score. So I would say that I have a standard score of 1.3, and what that means is that the 90th percentile lies approximately 1.30 standard deviations above the mean because it's a positive 1.3. So I need to put 1.3 and above. And for part C, same thing, except for this time I'm looking at the 17th percentile. So I go to the table, and 17%, I've got one that's 17.11. I'll use that. My z-score is negative 0.95. So that would be my first answer. And what that means is that the 17th percentile is 0.95 below the mean. So you need to put in the 0.95 and you need to put in the below. Okay, be careful on that one. Let's see. So that was number 27. Number 28 is exactly the same thing. And I'm not going to go through all of those again. So if you're on number 28 and you have questions, go back up to number 27 because they're the exact same problem. All right? Okay, number 29. An experiment consists of drawing one card from a 52-card deck. So one card from 52. What is the probability of drawing a black? So the probability of getting a black card. Well, remember to do probability, I pick the total number of cards and put it on the bottom. So there's 52 cards. How many of them are black? 26 of them. So my probability is 1/2. 1/2. Don't put it in as a decimal. Put it in as a fraction. It's not going to be happy with a decimal answer. Okay, number 30. An experiment consists of... Sorry, turn down the heater a little bit. An experiment consists of drawing one card from a 52-card deck. What's the probability? Oh, my number 30 is exactly the same. It's exactly the same question. So we're not going to do number 30, but if your number 30 is different, same idea. So number 31, determine whether the following individual events are overlapping or non-overlapping. Okay, are events overlapping or not? And it says to draw, for me, a heart or a diamond. Okay, well, overlapping means that you can get both. And hearts and diamonds are two completely different cards. You can't get both. Okay, you can't get both of those cards. So these are non-overlapping events. Okay, they do not overlap. And then it wants the probability of this happening. Well, there are 13 hearts in a deck, and there are 13 diamonds in a deck. So when I add that together, I get 26 out of 52 cards, which is, again, 1/2. That matches what we had before. Okay, number 32. This is a good one, and this is one that you're going to want to make sure that you understand. So this is if I randomly select, I meet a family with 3 kids. It says, what's the probability that there is exactly, there is exactly 1 or 2 girls. Now, I gave you a formula to do this because if this was your question, if you only had to figure out the family of 3 kids, that's easy. You can handle that. But some of you are going to have to do this with a family of 6 kids. So I gave you a formula in class to use that makes this a little bit easier. Now, you're always going to have 2 different numbers of girls or boys or whatever. So remember, the formula is you take the number of kids, factorial, divided by the number of girls, factorial, multiplied by the number of boys, factorial. Then you're going to add the number of kids, factorial again, divided by the number of girls, factorial, times the number of boys, factorial, all divided by 2 2 raised to the number of kids. Now, I know this looks like you're just doing the same thing twice on the left and the right, but this one is when you have 1 girl, and this one is when you have 2 girls. So when I plug in my numbers, I have 3 total kids, and first I want 1 girl. So 1 factorial multiplied by, well, if I have 1 girl, that means I have 2 boys. So 1 factorial multiplied by 2 factorial, plus I still have 3 kids, but this time, what if I have 2 girls? So 2 factorial multiplied by 1 factorial, all divided by the 2 raised to the number of kids, so 2 to the 3rd power. Now, this is why it works really easy if you lucked out and you got the question that only had 3 kids. Because look at how easy these numbers are. 1 factorial is just 1. 2 factorial is just 2. 3 factorial is just 2 times 3. So if you have a small number of kids, this is a really easy problem to do in your head or to do by hand. If you have the family of 6 kids, this is a lot messier, right? So if I had a family and it said there are 6 kids, what's the probability of getting 1 or 2 boys? Then my formula would be 6 factorial divided by, well, if I have 1 boy, that means I have 5 girls multiplied by 1 factorial plus 6 factorial over 4 girls and 2 boys, all divided by 2 raised to the 6th power. Those numbers are not nearly as nice to work with. This is a formula you really want to know for the next couple of weeks. So copy that down. If you need help getting it on a formula sheet, let me know, and we'll track down that formula for you and make sure that you have it when it comes time to. Again, if everyone was given the same question on this one, I wouldn't worry about you memorizing a formula. But the fact that some of you are going to get the 3 kids and some of you are going to get the 6, having to write out all of those solutions becomes very unfair. So we're not going to worry about it. Number 33. Holy cow, guys, this is a long review. You are given 3 to 2 odds against tossing 3 tails. So 3 to 2 odds against 3 tails in 3 tosses. And then it goes on to tell you what that means. That means if you win, you get $3. If you lose, you have to pay $2. Find the expected value of the game. So expected value, remember, you take the probability of something happening and you multiply it by the amount of money you win if it happens. So the probability of winning, of getting 3 tails in a row. Well, the probability to get 1 tails, you have a 50% chance. To get tails again, you have a 50% chance. To get tails again, you have a 50% chance. So that becomes 1 over 8, which is, that becomes 1 over 8. Yeah, we're at 1 over 8. And then you have a 1 in 8 chance of winning. And if you do win, you get $3. So I would take that 1 in 8 probability and times it by 3. So that gives me 3 over 8. Okay. Now, the probability of losing, if I have 1 out of 8 chances of winning, that means I have 7 in 8 chances of losing. And if I lose, I have to pay $2. So that's going to be 14 over 8. But this is winning money. This is losing money. So when I win money, I make it a positive. So I've got a positive 3/8. When I lose money, I make it a negative 14/8. When I combine these together, I end up with negative 11/8, which is like negative 1.38. So that is my expected value. I expect to lose $1.38. Now, the question goes on to say, what would you expect to win or lose money in one game? Win or lose in one game. And we got to be careful with this because we know that we have a lot better chance of losing than winning, right? But you can't predict what you expect to happen in one game. Okay, your answer should be, I would expect neither. Because the outcome of one game can't be predicted. You know what the chances are, but you can't predict the outcome of the one game. Okay, then the second question, it goes on to say, would you expect to win or lose in 100 games? Well, if I did this 100 times, I would expect to lose overall. Because my expected value is a negative amount. So, you know, if I flip a coin, if I try this one time, I've got 1 out of 8 chances of winning. But if I try this 100 times, that's 7 out of 8 chances of losing 100 times. So it's a lot easier to do expected value when you're doing multiple attempts, not when you're just doing one, okay? All right, so number 34. Same idea. 34 says someone gives you 15 to 4 odds that you can't roll 2 even numbers. So 2 even numbers with 2 dice. All right, so if I win, I get $15. If I lose $4. So my expected value, what are the chances of me winning? Well, I'm going to roll 2 dice, and half of them are evens on my first dice. Half of them are even, so I have a 50% chance of getting an even on the first one. I also have a 50% chance of getting an even on the second one. So that gives me my probability of getting 2 evens is 1/4. And if I do that, I win $15. So I would times that by 15. So that's 15/4. Then, if I have 1 out of 4 chances of winning, I have 3 in 4 chances of losing. So I'm going to times that by 4, because if I lose, I have to pay $4. And that comes out to equal 3. So to get my expected value, I would take what happens if I win, I get 15/4. What happens if I lose 3. So 15/4 minus 3 equals 0.75. My expected value is a positive 0.75. So should I expect to win the first game? No. You cannot expect to predict the outcome of one game. Okay, so no, you can't predict one game. What can you expect if you play 100 times? Well, if I expect to win 0.75 and I play 100 times, then I can expect to win $75. That's how that works. My expected value is 75 cents, and I'm going to play 100 times. So overall, I expect to win $75. Okay, where are we at? What number was that? 34? Number 35. We're coming to a close in 15 more questions. Answer the following questions using arrangements with repetition, permutations, or combinations. Okay, so this is taking us back to our formula sheet a little bit. It's been a while since we've looked at that thing. Now, a few things to remember. A permutation is when order matters. Okay, if I'm going to pick 3 people to be president, vice president, and secretary, it matters which one I pick for which. Okay, a combination, the order does not matter. Okay, if I'm picking a committee of 3 people to vote, it doesn't matter which order I place them in because they're just a committee. All right, it's kind of like the difference between if I pick 5 people to start a basketball game, it doesn't matter which one I pick to be number 1 or number 2. But in baseball, if I'm picking a batting order, it does matter what order the people bat in. They're different, okay? So on number 35, it says the president must assign ambassadors to 3 different foreign embassies. If there are 11 candidates, so I have 11, pencil, I have 11 candidates, and I need to pick 3 ambassadors. How many different diplomatic teams can she form? Now this one, I have a little bit of, I'm not sure how I feel about this one because it doesn't tell you if the order matters, and you kind of have to logic your way through it. And in this case, the order does matter because if the president assigns, if I've got country A, country B, country C, and if I assign people to different countries, that's a different assignment. It's a different team because they're in a different country. So I have a little bit of I don't like this question very much. I wish I could throw this one out. But we can't. This is one that the college chose. So in this case, order matters. And you can't pick the same person to be more than one diplomat. So I'm going to use my permutation formula. And that's on your notes. Permutations, it's the one that has a little n, a big P, and a little r. And it's n factorial divided by n minus r factorial. Okay, so to do that, n is my number of people. R is the number that I'm choosing. Okay, that's how many I'm choosing. So I have 11 people, and I'm choosing 3 of them. So I'm doing 11 factorial divided by 8 factorial on my calculator. So to remember to do that, I can make a fraction. And on top, I do 11. And then to do factorial, I click on Math. And I go over to Probability, PRB. And I go down to Factorial. And then on the bottom, I've got 11 minus 3. And then I'm going to do factorial again. And I get an answer of 990. Now, I could also use, you are more than welcome. Let's see, where's my probability on this one? Math, if I go over to PRB, oh, right there, NPR. I can choose NPR, and I can put in 11 and 3 like this, and it'll do the math for me. I don't care which way you do it. I just care that you know how to do it, okay? So there are 990 different diplomatic teams that this president could put together. All right, 36. Answer the following questions about arrangements, repetition, permutations. How many anagrams of the letters, let's see. So for me, it says cam phone. Is that a word? Can you make? All right, so for this one, here's how I would do this one. it's kind of a permutation, except you can't really use the permutation formula, okay? So I have 1, 2, 3, 4, 5, 6, 7, 8. Wow, I almost skipped 7. I have 8 letters that I'm picking. So I'm going to do this the old-fashioned way. I'm going to do this just multiplying it myself. The first letter, when I rearrange these, I have 8 choices of letters that I can put in the first spot, right? Because I'm going to have 1, 2, 3, 4, 5, 6, 7, 8 spots to put a letter. I've got 8 letters to pick from for the first spot. I have 7 left to pick the second spot. I have 6 for the third spot. I have 5. So as I go down the spots, each time I lose a letter that I could put there, right? Well, to get my answer, all I'm going to do is multiply these together. So really, my answer is just 8 factorial. 8 times 7 times 6 times 5 times 4. And when I do that, I get 40,320 different ways that you could arrange these letters. Okay, number 37. A DJ is preparing a playlist of 24 songs. So 24 songs, all right? How many different ways can they arrange the first 6 songs? Well, order matters because they're wanting to arrange the 6 songs, and it's different if they get played in a different order, right? So this is going to be a permutation. And these numbers are really big. So for permutation, n factorial over n minus r factorial. Or you can use NPR. So I've got 24 songs, and I'm going to pick 6 of them. So that becomes 24 factorial over 18 factorial. So on my calculator, I can do 24 math factorial divided by 18 math factorial. Or I can use my NPR button. NPR 24, and I'm choosing 6. Either way, I get the same answer, which is going to be 96,909,120 different ways that you could play the first 6 songs if you were only choosing out of 24. That's insane. 96 million different arrangements. Does that make a DJ's job sound harder? Not really. You're picking songs and you're playing them. Okay, number 38. A king in ancient times. All right, so this is our classic chess question, and it's going to ask me 2 things. Part A asks me how many grains of wheat on square 21. Part B is asking me the total grains after 21, after square 21. And then part C wants the weight. So 3 questions, 3 different formulas. These are other ones that I've kind of shared with you. In order to find the grains of wheat that should be on square 21, just square 21, I use my 2 raised to the n minus 1 formula. So I would do 2 raised to the 21 minus 1, which is 2 raised to the 20. And if I do that, 2 raised to the 20, I get 1,048,576. So 1,048,576 grains on just that square. I don't think they're going to fit. To find the total at that point, I still do 2 to the n, but the minus 1 drops down here. 2 to the n minus 1, which is 2 to the 21 minus 1, which when I plug that in, 2 raised to the 21 minus 1. I got to make sure the minus 1 is down below, which it is not. There we go. Minus 1. 2,097,151. Holy smoke. Okay. 2,097,151 total grains. Now to figure out the pounds, how much that weighs, it tells me that a grain is 1 over 7,000 pounds. And it wants me to measure in pounds. Okay, I can do that. So if I have 2,097,151 grains, and I times that by 1 over 7,000 pounds, then my answer becomes, or I can divide it by 7,000, which is probably what I would do. Divide by 7,000. Nope, not 7,000. 7,000. 299.593. So 299.593. And it wants me to round to the nearest tenth. So 299.6 pounds, right? Okay, number 39. Same question, but this time it wants to know the weight that will be placed on the first 61 squares in tons. Okay, so 2 to the n minus 1, because it wants the total. So that's going to be 2 raised to the 61 minus 1. So let's start there. 2 raised to the 61 minus 1 is a great big number. I'm not going to copy that down. That's how many grains of wheat we've got. So then I'm going to take that number, and it wants me to convert it into tons. So the first thing I'm going to do is divide it by 7,000. Okay, so I'm going to divide by 7,000 because I'm going to turn it into pounds. Now I've got my pounds because it tells me that, where does it say? 1 ton is 2,000 pounds. So 1 ton is 2,000 pounds. So now to turn it into tons, now I'm going to divide it by 2,000. So divide by 2,000. And I get a great big number. 1,647,03,07,20,86 point blah, 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 blah. Okay. It wants the total weight. Use scientific notation. Then round to 6 decimal places as needed. Okay. So I only need the first. Let's take the first. This is a lot of numbers. 164703. 164703. 07208. 07208. 6.69. 6.69. Okay, so it wants me to write this in scientific notation, which means I don't have any e's there, right? I'm going to take this decimal. Whoops. I'm going to take this decimal, and I've got to move it all the way to here. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it's going to be 10 to the 11th power. And then it wants me to round to 6 decimal places. Well, if this is my new decimal right here, then I'm rounding 1, 2, 3, 4, 5. I'm rounding to that spot right there. So I'm going to look at the 7. That tells me I need to round up and turn this into a 1. So I'm going to put 1.64703 times 10 to the 11th power. Yeah, there's a lot that goes into that question. So be careful with your rounding and your scientific notation. They're good questions. It's a great one. You just got to follow the steps carefully. Okay, we are number 40. The end is in sight. The initial population of a town is 3,000, and it grows with a doubling time of 10 years. All right, so I'm going back to my formula sheet. And this time I'm using, what am I using? Doubling time. So I initially started with 3,000. That was my population. And it has a big T doubling time of 10 years. What will the population be in 8 years? Remember, time is little t, doubling time is big T. So the formula that I'm going to use, my new value is equal to my initial population times 2 raised to the little t over big T. I probably should have written that out. My new value equals the initial value multiplied by 2 raised to the little t over big T. And I didn't even put big T right there. It's 10. So 3,000 times 2, so 3,000 times 2 raised to the 8 over 10. When I hit enter, I get 5223.303. 5223.303. And it wants me to round to the nearest whole number. So that's going to be 5,223 is going to be my new population. Okay. Number 41. The number of cells in a tumor doubles every 3.5 months. I like this one. I like this one because of the way that it uses the months, right? It's using, well, I guess we're just going to turn everything into months is what I'm trying to say. Because usually T and big T are in years, but it gives me some of my information in months. So I'm going to turn everything into months. So if I start with a single cell, so my new value equals my starting value, which is 1, multiplied by 2 raised to the little t. Well, it told me that my doubling time, big T, is 3.5 months. Little t, for the first part of the question, is 3 years. But I want to change that into months. So that's 36 months. So I'm going to put 36 on top and 3.5 on the bottom because now my units are the same. Okay, so I'm going to do 1 times 2 raised to the 36 divided by 3.5. And I get 1248.269. So 1248.269. And it wants me to round to the nearest whole number. So 1248 would be my answer for the first part. Then it wants to know after 4 years. So my new value is still equal to 1 times 2, but this time I'm gonna go for 4 years. 4 years is 48 months divided by 3.5. So 1 times 2 raised to the 48 divided by 3.5. And I get 13,440. 13,440. Since I'm rounding to the nearest whole number. Okay, number 42. If you're still here, consider the graph, identify the independent and dependent variables, describe the function. Okay, independent is the x-axis. Dependent is the y-axis. All right, so whatever's going across the bottom. For me, across the bottom is my independent variable is years. And my dependent variable going up the y-axis is population. Okay. Now the domain of the function is my x values. My domain goes with my independent variable. And I go from 19, let's see, for me, my lowest x value is 1950, and I go up to the year 2000. So that would be my domain, 1950 up to 2000. My range is my dependent variable. And on my graph, the lowest is 2, and it goes up to about 6. All I have to do is read the graph, okay? Then describe the function in words. I think you guys can handle that one. All right, number 43. The following data table represents a function. Identify the independent and dependent, and describe the domain and range. Okay, so for me, my problem, it gives me speed, and then it tells me miles per hour, and then it gives me stopping distance. And it just gives me that in feet. Okay, so it doesn't tell me which is which, but if I look at this, is my speed going to affect the distance it takes me to stop? Or is the distance it takes me to stop going to change my speed? Clearly, your speed is the independent and your stopping distance is the dependent, because stopping distance depends on how fast you're going, all right? Now, my domain on my graph, or on my list, my data, my lowest speed is 10, and it goes up to my highest speed, which is 70. And my range for my stopping distance, my lowest is 9, and it goes up to 311, okay? And then again, you can describe that one in words on your own. Number 44. Suppose you magically tripled in size. I love these questions. I really do. I like these ones. You tripled in size. So your height, weight, and depth go up by a factor of 3. What factor has the amount of material for your clothes increased? So we're looking to see how much has our material for our clothes gone up. Well, remember, if I'm going up by a factor of 3, then my clothes are area. And when I go up by a factor of 3, I have to square it to get my area factor, which is 9. So my clothes would go up by a factor of 9. If I tripled in size, I would need 9 times as much material to make my clothes. Okay, number 45 says that you quintupled. So you went up by a factor of 5. What factor has your weight increased? Okay, well, weight is volume, and volume increases by a cube factor. So I have to take that 5 and cube it. So if I got 5 times as big, my weight would be 125 times what it started as. If I got 5 times as big, my weight would increase 125 times. That's a big boy. Okay, number 46. Make a tiling of the using translations only. So your original shape is going to look something like this. And remember, to make a tiling, you can't flip it. All you can do is slide it left, right, up, and down. Okay, so I can take this same shape and I can slide it over to the right, or I could slide it down, straight down, and it's going to make a tiling. So what you're looking for, what makes this one a little bit hard, is it's going to be boxed in like this. So sometimes it's hard to tell if it's been flipped or not. So just look for the one where you can take your original shape and plug it in somewhere without flipping it. Okay, number 47. And that would be a good one to know how to do, guys. 47, identify all the symmetries in the following figure. Okay, so depending on your figure, remember that the reflected lines match how many points there are on your shape, okay? So my shape, and I wish you could see this, my shape, it has 8 points. It's one of those that has, it's like a circle. but it's not a circle. It's missing some of the pieces. So it looks something like this, except that it's drawn. You know what? That's not too bad, except for this weird gap at the top. But, you know, not all dandelions are perfect, so leave it alone. I count the number of points, 1, 2, 3, 4, 5, 6, 7, 8, and that gives me my reflected lines. So I can say there are exactly 8 lines that it can be reflected across. Okay. Now, as far as rotations go, to figure out my rotations, I'm going to take 360 degrees and divide it by my number of points and get 45 degrees. So 360 divided by 8 gives me 45. That tells me how I can rotate my shape without changing my shape's appearance. So I can rotate my shape 45 degrees over and over and over as many times as I want, and it's going to be the same shape. So I can say that it can be rotated through any multiple of 45 degrees. And remember, the translated one, even though it seems like it should work, it doesn't work. So those are going to be the only 2 answers that I use. Number 48, make a tiling. You're not watching this video for help with number 48. You guys all got number 48. 49, the sides of a rectangle are given. Compute the ratio of the long side to the short side. Is that ratio a golden rectangle? Okay, so it wants me to compare the short side to the, the long side to the short side. And my rectangle looks something like this. This is 4, and this is 6.4. And I love that on the picture, it's definitely not drawn to scale. You have to look at the numbers. So my long side is 6.4. My short side is 4. If I divide that, I get 1.6, which is approximately the golden ratio. It's not exact, but it's close enough that it's going to look good, which is what we care about. So I would say yes, it is close enough to a golden rectangle. So yes. Number 50. The length of one side of a rectangle is 6.9. Find the length of the other side. Oh, a golden rectangle. Notice that, so I have a golden rectangle, and this side could be 6.9. Or I have a golden rectangle, and my short side is the 6.9. And it wants me to find out what the other side would be. Okay, so part A, if 6.9 is the long side, then 6.9 divided by the short side, that's not a 5, that's an S, divided by the short side has to equal 1.62. That's what it tells me to use for my golden ratio. So to figure out what's on the bottom, I've got to do my railroad track thing. It's been a while. I'm going to multiply S on both sides. So I get 6.9 equals 1.62 S. And then I'm going to divide by 1.62 to get my short side. So 6.9 divided by 1.62. 6.9 divided by 1.62. Enter 4.259. 4.259. And it wants me to round to do 2 decimal places. So 4.26 would be my short side. Now, what if 6.9 was the long side? So part B says, what if 6.9 what if 6.9 is the short side? So I'm looking for the long side. 6.9 is the one on the bottom. So to do this one, I still do railroad tracks. I just have to times by 6.9. So 1.62 times 6.9 is 11.178. But it wants me to round to 2 decimal places. So right there. So 11.18 is going to be my answer for that one. Okay, that was a lot of math. We will be testing in class on Friday, but the test is open as of tomorrow. So if you're ready, go ahead and get started on that test. You're more than welcome to take it before Friday.